他的天后我来我们这边演讲，那他讲的题目会关于那个定量降水估计。那他看到说 So that's welcome, Dr. Campbell.
Well, that was a very interesting talk that Fantoon gave. Sitting in the back of the room watching it, I was starting to get a little woozy from the thing. I brought up a website. This is a live website that some of the imagery that he was showing on the sphere you can get from this website. This is the MODIS website. The two satellites, the Terra and the Aqua satellite, they post the imagery, and you can go look at the imagery and as well as retrieve the very high resolution imagery. Like for example, this is 250-meter resolution. You can go and retrieve the images in real time. As the satellite passes over Taiwan, you can, on your laptop, extract the images. It's a very powerful...
You want the microphone?
You want me to use the microphone? Does that help? Can everybody hear me now? Better? Okay. On the MODIS website, there are many typhoon images, some very interesting typhoon images to look at as they approach Taiwan. I would really strongly suggest everyone go look at them because there's some very interesting things that you can see. Since we have internet, I went ahead and brought up a web page that we have in the US for a project that we call NMQ. And you can grab the address, it's not protected, and I can share it with you after the presentation. The NMQ project is a research and development project and system that we've set up in the US to develop new QPE and very short-term QPF techniques. It is a test bed on a national scale. And I'm just going to briefly cover a little bit about this because the things I'm going to show you about this system is going to happen in Taiwan over the next couple of years. We will be installing a very similar system here at the CWB. What this system is doing is we're ingesting all of the weather radars in the United States, all the network radars, which comes out to be about 146 10-centimeter radars in real time. We're ingesting those radars back to Norman, Oklahoma, which is located in the central part of the state. We're using the internet to transmit the base level Doppler radar from all of these radars in the US. And then what we do is we mosaic all of these radars together. We develop a three-dimensional mosaic. Now, we're doing this in real time, and I'm going to show you some of these products in a real-time mode. This is a squall line that's moving through the eastern part of the United States. This image is a real-time image. We process all of the 140-some radars in real time every 5 minutes. And we do it at a 1 kilometer by 1 kilometer resolution. Each one of these pixels is 1 kilometer by 1 kilometer. It takes, we have a cluster of computers. It takes less than 2 minutes for us to process the entire US and to generate the various products. This is a composite reflectivity, a standard three-dimensional composite reflectivity. But when the data arrives to us, the data is in its raw form. So it has all of the AP biological targets, sun spikes, all of the issues that you have to do with the radar data. So the first thing that we do with the radar data is obviously to do quality control. So we take this image and turn it into that image. To try to remove all the non-meteorological targets, because we want to generate a QPE from this. The next step in generating a QPE from this product, from all of the radars, is that we want to go through and take a look at the three-dimensional structure and identify where we think different types of precipitation is occurring. So what we do is we go through and we identify where we think we have convective precipitation processes, where we have tropical, where we have frozen, as well as the quality of the precipitation that we think is might falling, whether it's contaminated or whether it has bright band problems with it. And we do a classification. Then from that...
Can I ask a question?
You bet.
How can you put a word like good or bad on that?
Excuse me? Okay.
Good and good represent bad.
Okay, what we do is we calculate whether or not that particular pixel is contaminated by the bright band. If it has bright band contamination, we classify it as bad rain.
That's a quality.
Yeah, it's a quality control. So before we assign, we don't want to assign a rain rate to an area that is being contaminated by the bright band. Okay? From this, we then compute a rate. Based upon the classification of what type of precipitation we think is occurring, then we go ahead and compute a rate from that. It'll come up. There we go. So then we compute a rain rate, shown here. So based upon the precipitation classification field, then we go back to the reflectivity and apply a rain rate. And then from that rain rate, we obviously can do accumulations of whatever time period we want. So we can do a accumulation up to 2472 hours. Now, this page is experimental because one of the things that we're interested in finding is how to deal with all of the interesting artifacts that come up in the radar. Okay? It is a very difficult challenge just to use a radar to compute rain rates without starting to find some of the different artifacts from everything from areas that you're blocked in to calibration differences. This is an example here of a calibration difference between two adjacent radars. So many artifacts that we have to overcome. And so things that we do is, for example, we bring in such things as other types of remote sensors. So here's an example where we take a satellite and we use the radar information to calibrate the satellite. So here you get a much more seamless, cohesive field that doesn't have all of the artifacts that the individual radars have. And so this is what we call a multi-sensor approach, where we try to take and use satellite, radar, surface information, model information to try to do the best depiction of QPE that we can. And so I'm going to leave this live website. I would encourage you to come look at this. Feel free to send myself or Jin questions about what you're seeing on there. There's many different things, and I'll be glad to talk to anybody about what's on this web page. But it's.
Huh? You also have a gauge category, right? Gauge, rain gauge.
We have gauges now.
But is this data already have gauge data in?
No.
No.
Here's
so the one earlier.
Here's our philosophy. Our philosophy is that our focus is on very small time and space scales. We're trying to get towards flash floods. The gauge reporting network in the United States is not nearly as robust as Taiwan's. And so what we have to do is do the best QPE we can without the gauge data. Now, we run the system two ways. We run the system one way in that if there is gauge data available, we'll use it. We have a suite of products. All of these are the different QPE products, and where you see a GC after the name, at the end of the name, that's a gauge-corrected product. Okay? The GC at the end. So for example, I'm going to drop down and do the latest. For example, this product is a gauge-corrected product. Okay? Uses a local gauge correction. And we do this one 6 hours behind real time, because that's how long it takes for all of the gauge data to trickle in. So we run parallel processes where we run in real time, and then we run 6 hours behind to do this. But in Taiwan, you have a different situation in that you have, over 450 gauges report about every 10 minutes. You can do a gauge correction in real time fairly easily. So I'm going to talk a little bit about the HRQ2 project as it pertains to Taiwan. And I'm just going to show you, as far as time, I'm just going to quickly take you through some of the products and some of the research we're doing, and then a little bit about our future plans as far as what we're going to implement here in Taiwan. My quick background is I'm a research meteorologist and a program manager. I worked for 11 years for the same laboratory that Fan Toon worked for, and I've been at NSSL for the last 14 years. My specialty and interest is in hydrometeorology decision support systems. I'm involved in doing UAV type technologies as far as autonomous aircraft and gliders that we use on weather balloons. I also do work using portable Doppler radars. This is one in the Southwest. And then I'm also a photographer. I'm an amateur photographer. And this is I love coming here because it's an opportunity for me to take pictures. Jen and I are both from NSSL. Here's our website. I encourage you to go look at it as far as the spectrum of technology that we do. Okay. I'm going to teach you 4 principles that will go with you the rest of your meteorological life. And these 4 principles you will not read in a textbook. And your fantastic professors will never tell you these things, but I'm going to. So, okay, so you ready? We're talking about the 4 laws or 4 principles of hydrometeorology. The first one should be fairly obvious. Flash floods occur where it rains the longest and the hardest. Very simple. So where does a flash flood occur? Where it rains a lot in the same place. Second one, it rains the longest and the hardest where you have the fewest observations. Okay, remember that. Where does a flash flood occur? In a place that you don't have many observations. This is a very important one. Water travels downhill. Okay? Now, you should be able to guess the next one. The steeper the hill, the faster the water runs. Okay, So between the first one and the fourth one, you know everything you need to know about hydrometeorology for flash floods. Okay. Well, to be fair, let's talk about the one law of nowcasting. Okay? And for those of you who want to be meteorologists, I encourage you for the rest of your life to heed this law. The best nowcast is derived by looking out the window. Never issue a forecast unless you look out the window first. Okay? Very, very important. There will be a quiz at the end of this seminar. Okay. I always show this one because, you know, coming from the United States, we think everything happens in the United States, and we have the severest weather and the most extreme temperatures. But very few people really understand that when you take a look at the frequency and the magnitude of tropical cyclones, and you look at where Taiwan is, this is one of the toughest places in the world as far as dealing with extreme weather. Okay? So, for us, for Jin and I, this is quite exciting. A good scientific challenge for us to come out here and take a look at some of the processes. What I have here is an hourly loop of composite reflectivity from this past summer. And I show this because I want to show that as far as precipitation falling in Taiwan, you can get it a number of different ways. Whether it's a traditional Mayu front, whether it's a shortwave coming by, whether you have orographically forced precipitation or thunderstorms, and then the most frequently associated with this is our nice typhoons as they come by. So you have a whole spectrum of how we can get precipitation in Taiwan. And when I look at this from an artistic standpoint, I always say it looks like the dragon licking Taiwan, the fire licking Taiwan. The work that we've been doing out here for the last 3 or 4 years has been focused on enhancing the monitoring prediction of precipitation, flash floods, and severe storms for the Taiwan environment. We've been involved in a collaborative research project for the development, refinement of operational product generation. What we in essence have done is set up a system here at the CWB in collaboration, an end-to-end system that goes from the raw radar data and other data sets to generation of operational products that are focused on QPE and very short-term QPF. The primary area that our research is focused on is the current hour and out to 1 hour, where our focus is on seamless high-resolution QPE and very short-term QPF, and we're doing it at a resolution of 1 kilometer with a 10-minute update cycle. The system that we have set up that's evolving over the next year consists of 4 different components. Primarily, the first component is a data ingest system that ingests the radars, lightning data, satellite data, upper air data, model, surface observations, primarily rain gauges, and does a quality control and data integration. From that, we build very detailed 3D mosaics of the radar data, and then generate a suite of QPE and short-term QPF products. Then the CWB maintains and operates a dissemination system using a web browser that was developed back in Oklahoma. And then the last system is a verification and assessment system. It allows us in real time to look at how the different algorithms are performing based upon the gauges. The images that I'm going to show you and previously showed you are from these 2 systems right here. In addition to the regular radars, the systems also has the ability to ingest portable radars as well as dual polarized radars. The product generation, the principal pieces that are used in the product generation are obviously the 471 rain gauges across Taiwan and the 4 major radars that are across here. Taiwan has probably the most dense rain gauge observing network in the world with the exception of Japan. It's a perfect opportunity for research to be done and looking at rain gauge radar sensitivities. Now, why do you want to integrate the data? Well, if you take a look and just use one radar, you only get partial of the picture, but if you start using all of the radars and be able to mosaic them together, you get a more complete picture of the phenomenon you're interested in this case, a typhoon. Now, why is that important? Well, because it's important to understand how the typhoon is evolving so you can get a better idea how it's going to track and move. And this is a track from Haiting. And one of the things that I want you to pay attention to as far as this goes, if you're a forecaster and you're looking at the track up to this point in time right here, what is your simple extrapolation going to be? That is it going to continue to move that way. But with the radar data and the being able to mosaic the radar data, we get a better idea that it didn't move that way at all, but really tracked this way. Can the models capture this? Not quite yet. Most of the models will try to take this and do just basically a linear extrapolation. But having the typhoon curl like this produces copious amounts of rainfall in Taiwan. So it's important to be able to really track accurately which way the typhoon is moving. One of the issues we talked about, and I showed you from the NMQ system, is quality control. Tremendous problem in Taiwan is to clean up the radar data and remove non-meteorological targets. Here's an example of a technique that we've been working on as far as removing coastal AP from China. This is a before, this is an after picture. Here's another example, before and after. Yet it's not perfect. We still have some issues associated with some AP. We're now working on a satellite technique where we're bringing in the satellite data, co-locating it with the radar data to try to start removing it. So like here's the before picture. Here's using a simple radar algorithm to remove the AP, to identify and remove AP and non-meteorological targets. And then this is bringing in the satellite data at the very end to try to clean up the data completely. But we still have some issues with some residual data. So one of the research projects that we're working on is using a neural net to be able to do a better job of QC here in the Taiwan environment. This is a 24-hour loop of composite reflectivity from the 27th of May of this past summer. I'm just going to show you the very basic steps that we go through for generating a QPE. In Taiwan, I would pay attention to this area right in here. We saw kind of a quasi-stationary convective line set up. If you take the gauge data by itself and then do an interpolation, this is basically what it looks like. Okay? This is only the gauge data doing an interpolation among the rain gauges. This is the radar data for the same time period accumulation as the rain gauge data. For one thing, you can see that you have a lot more detail with the radar data, you have a lot more information with the magnitude, a lot more information as far as the gradient, but you can see there's a problem with the magnitude that doesn't quite match up to what you're seeing with the radar, or with the gauges by themselves. So if you do a scattergram and plot up the gauge amounts versus what the QPEs from the radar is, you really don't have, you have quite a bit of scatter. If you had a perfect match, obviously they would be right along this line. So here we have an overestimation. If we take a look at the total bias, we have an overestimation of fairly poor correlation coefficient. Well, that's really not suitable for operations. You want something a little bit better. Now, if you take the rain gauge data and use it to do a local gauge correction onto the radar data, this is what you get here. So you keep with the radar data, you keep the very nice gradients and the very fine detail, and then you improve a little bit on the magnitude. So here is the scattergram for the local gauge correction, and you can see we do a much better job of getting those two correlated. operation. It's really doing a systematic evaluation to looking at the radar-only QPEs and how they vary with different types of phenomenon to get a handle on where we do well and where we don't do well. So here's kind of the initial results from this study. There is no systematic bias. Okay? That's kind of good. If you're not systematic bias, you mean, in other words, we're not always overestimating and we're not always underestimating. So the estimates are somewhat dynamic. It kind of adjusts to the meteorological situation. However, the general estimation in regions of deficit radar coverage, pretty obvious. You don't have good radar coverage, your estimates are not going to be that good. You have a tendency to underestimate. We also have underestimation characterized by orographic enhanced precipitation. One of the biggest challenges in Taiwan is capturing the microphysical processes associated with upslope or orographic forcing. We also have a problem with overestimation as a result of convective brightband contamination. And that's true for places in the US. So one of the questions that somebody could ask is, with this very high dense rain gauge network, why do you need radar? Okay? Because you have this very, very dense. So in other words, does the radar still bring some value to your QPEs? And this is a study that Bao Yang has done from the CWB, where he looked at the local gauge corrected radar estimates and also looked at the gauge only interpolated estimates. And he did a sensitivity study where he took and started removing the number of gauges in each one of his analysis. So he started off by removing 50 gauges, did a local gauge corrected radar, did a gauge only. And he did it for two types of events, southwest flow and a typhoon high-ting. So the solid lines are the local gauge corrected radar for these two types of phenomena, and then the dashed lines are the interpolated gauges only. So what it's showing here is that as you continue to remove the number of gauges, in other words, you make the gauge number less dense in time, your estimates start rapidly decreasing with just using the gauges only. But your radar information, you still have value. So this is, to me, a fairly landmark piece of research that's being done here in Taiwan that really shows the value of the radar, but also shows you the strength of combining the radar with the gauge network. And there's a whole set of products that I'm going to quickly step through that the CWB has developed using the QPE technique that I just went through. And this is, for example, showing the max rainfall per county accumulated over different time periods. Another example is doing area QPE accumulations. This is the actual QPE amount, and this is it accumulated on a county level, on a basin level, on a sub-basin level. And this is a very short-term QPF. There's two types of QPF that we can do in Taiwan. There's a QPF that you can do by a model. This is an atmospheric model. And then there's a QPF you can do by doing an interpolation or convection of the reflectivity field or your precipitation field. For Taiwan, you need to do both because both of them work well at different time and space scales. A simple advection technique works well when you're trying to do flash flood forecasting, as far as trying to do something that's occurring at very small time and space scale. Because it takes a while for a model to spin up to generate a QPF. So this is a very simple advection scheme where you're taking the rainfall and you're advecting it over time and accumulating it. And so here's another example of a short-term QPF where you're just advecting it, but you're doing it where you're accumulating it on very small basin scales. And this is important for doing mudslides or landslide type thing, as well as flash flood prediction. And here's kind of an example where you're taking and accumulating the rainfall on a very, very small areas on the sub-basin level to be able to really identify which areas are really at risk for flash floods. Okay? So the CWB has built a very nice system to being able to, for an operational system, to be able to try to work and identify where you have heavy precipitation that might be leading to flash floods. As well as they've developed some unique graphics as far as doing typhoon tracking and keeping track of where typhoons have gone. Over the next year, we're going to be upgrading the system. We're going to be doing a major upgrade to the system that we have at the CWD. The upgrade is going to be identical to the system that we have running in the US, with the exception of we have a much richer data set to work with here in Taiwan as far as the gauge density network. And part of this new system, we will be implementing a new type of neural network reflectivity QC application. We also will be computing vertical profiles of reflectivity and testing a VPR gap filling technique. We also will continue to build 3D reflectivity mosaics, but we're going to build these at 500 meter resolution. Right now in Taiwan, resolution is 1.3 kilometers. We're going to basically do roughly a 500 meter resolution for Taiwan. And I'll talk about why we're going to do that in a little bit. Then we're going to run a whole suite of QPE applications. In other words, we're going to do kind of an ensemble approach. We're going to start with a very basic radar-only QPE techniques, and then we're going to make it more and more complex by bringing in other different observations and other types of techniques for computing the rainfall. And then we'll generate some uncertainties associated with that. Here's an example of a multi-sensor neural network over the US. This is the before, this is the after, that's the difference. So one of the things that we'll be working on over the next year is training a neural net based upon Taiwan data, so that we can hopefully get this type of results over Taiwan. The other thing I talked about is that we're going to go to the 500 meter resolution. Now, given where the radars are located, given the geometry of the beams and the bends, it's very difficult to get a seamless 500 meter resolution over the country of Taiwan. Roughly where these circles are, about 70 kilometers, you can have a true 500 meter resolution associated with your radar data. And then when you get further out, and this white area here is an area that you're approximately between 500 meters and 1 kilometer. Then obviously when you get outside of that area, you're back up to greater than 1.3 kilometers. So we're going to be testing and evaluating running for the country of Taiwan, having our bin resolution at 500 meters and examine it. This is an example of a case study that's underway right now of looking at 500 meter resolution versus a 1 kilometer resolution. This is over central Taiwan. This is a 12-hour rainfall accumulation associated with Typhoon Haiting. And the thing that I want to point out to you, you can say, probably in the back of the room, you're going, wow, there doesn't look like much difference there. But what I want to point out is take a look at the gradient associated here. You have a lot more information about the gradient of the rainfall. You also have a little bit better delineation of what the magnitude is. This becomes quite important if you're trying to do flash flood forecasting, and you're taking a look at a QPE amount, and looking at the gradients where you have a very low amount here, a very high amount, you have a very tight gradient. What really becomes important if you're trying to do flash flood forecasting? You want to know where that rainfall is falling. So if I bring up the terrain information underneath, you see that that maximum is associated with a very complex terrain peak area here. That minimum is associated down with the valley, down here. So by doing the very high resolution and being able to map that to your detailed terrain information, you know which particular valley or particular area is at risk for either a landslide or a flash flood. And that's also important when you're looking at the urban environment, that you want to have very detailed rainfall estimates over the urban environment as far as helping the civil emergency people know where they need to evacuate, where the most of the rainfall is going to occur as far as causing flash flooding in the urban environment. So it's important to get down to that resolution. Is it going to be perfect? Absolutely not. it's going to take some time to improve the quality of the products. And so that's one of the reasons we're upgrading the system, because the new system that we'll be implementing with the CWB will have the flexibility for us to try new techniques. And I say, for us to try, doesn't mean just me or Jen. It means anybody in this room who's interested in trying to develop new QPE techniques or new QPF techniques. We're setting up a system that will allow all of us to work together to deal with this very challenging problem. And it also becomes very important to drop down to a finer resolution to be able to start taking a look at what the internal circulation of Typhoon is. To be able to understand how it's progressing in its strength. Dual polarization. You guys have more experience with dual polarization in the Taiwan environment. We in the United States have been working with dual polarization and are now in the process of upgrading all of our network radars for dual pol. And I think all of you have probably seen this diagram to understand the difference between conventional radar and dual polarization radar. Basically, a dual polarization radar, you're transmitting your signal both in the horizontal and the vertical, which provides you a little bit more information about the size characteristics of your hydrometeors. So what does that do? Well, it allows you to do a direct hydrometeor identification, where you can take a look at a cross-section of the storm and identify where you have light rain, heavy rain, where you might have hail going on, or grapple, dry snow, what types of wet snow crystals, to really start getting a look at where the different kinds of characteristics of the hydrometeors. Now, a lot of people, a lot of research that's been done on looking at dual polarization for improving QPE. Here's my opinion. The biggest benefit from dual polarization will not be from QPE. It will be from being able to do initialization of our models. Here's a very explicit 4D bar of what is going on that you need to initialize your models to do a better model performance. So the biggest benefit in my mind for dual polarization is not going to be for QPE, but for doing model initialization. The other thing that's going to be very useful for dual polarization, especially in the Taiwan environment, is for quality control. Being able to identify when you have AP or insects or birds or non-meteorological targets. Also, the dual polarization will be very useful for doing calibration. So if I were to do just a quick, and I apologize for this because obviously you know more about dual polarization potential in Taiwan. Here's my guess at what the benefits of dual polarization will be in Taiwan. One of the biggest benefits will be cross-calibration of the QPEs among the CWB radars. I think that's very important. Obviously, improved radar quality control for the identification of non-meteorological targets, gap filling for partial blockage things, and something that I think is dear to a lot of us in the research community, a better understanding of the rain microphysics in a tropical environment. Very little work has been done in trying to understand rainfall microphysics in a tropical environment. Most of the work is done in mid-continental type situations. Something that I'm very interested in and I've been proposing since the very first time that I got here in Taiwan, and that's the use of portable Doppler radars, to really start using them as a research tool to better understand the rain regimes that occur in Taiwan, the microphysics associated with the rainfall that occurs here, getting a better idea of what the typhoon internal structures are, as well as being able to use it to figure out where our rainfall estimates are being underestimated and why. And this is a simple histogram that shows that with a portable radar placed in a proper place, we can do a much better job of estimating rainfall than the standard radar network. So in closing, the project that we've been working on with the CWB has been really focused on high resolution and as accurate as possible QPE and short-term QPF. Again, I will emphasize, it's operational and it's not perfect. It's a work in progress. Okay? There is still a lot of research that needs to be done, a lot of techniques that need to be developed and tried to really improve QPE in the country of Taiwan and the surrounding area. And the emphasis has got to be on the multi-sensor approach. No single instrument will do the job as far as the many complexities to QPE and QPF in Taiwan. So it requires really a dynamic and continuous process of infusing new research and upgrading the applications. And as always, NSSL is very grateful for the opportunity to collaborate with CWB. And I put in here the university community. This is one thing that we really have not gotten to solidify, and you and I have talked about it many times, and I'm hoping that over the next few years we can really start solidifying, getting some of the university participation and the important research you're doing, getting us some feedback and start improving some of the applications with our new system. Okay, I threw this in here. I gave a seminar at the WRA, and one of your professors asked me if I could start over, where would I put the radars? Okay, so this is where I would put the radars. Okay, and I'll kind of give you a little bit of my reasoning why I would put the radars. First place, the last place you want to put a radar is a place that you're most interested in observing. In other words, you want to have the radar away from the area that you're very interested in observing. So, to me, to really capture the southern part complex terrain, you need to put the radar offshore on, I believe it's Green Island out here. And if there was another island over here, that's where I would suggest moving this radar as well. I'd also suggest putting your radars, a couple of radars, up on top of your mountains. Now, when you do that, the very first thing you want to do is you want to make sure that you can scan those radars below the horizon. Okay? Because typically what happens is, like Hoppenson, you put it on the mountain, but it can't scan zero and it can't scan down below. Yet, the most important information is down below. So it makes perfect sense to put the radars on top of the higher mountain terrain because you're going to have the most coverage. But operate them at 0 degrees and below the horizon. The radars can be operated observing below the horizon. Okay? Actually, there's a program right now. None of the radars in the United States operate below the horizon. However, over the next 2 years, they are testing to take 26 of the radars and actually operate them at 0 degrees and some of them below the horizon. The reason we can't do it in the United States is because of environmental concerns. So they're doing a major study to look at what are the real environmental issues with operating the radars. If they can get past the environmental issues, then about 20 radars in the U.S. will operate down below the horizon. If I had a magic wand, I would say the first thing I would do is I would operate Wolfenson down below the horizon. Because I think there's still useful information by operating it at 0 degrees and maybe at minus 0.1. Since the other thing is the YLAN radar, if I had my magic wand, the other thing I would do is I would take the sector block out. Because that radar, even though you have very complex terrain and you have ground clutter, I still think there's a lot of useful information in that radar to look at. And so I'm not sure. I think there's some environmental and some electronic interference issues with operating, with not being able to spin that radar or have the block out of there. But that, I think those two things will help improve things. But look, let's face the fact. To try to do QPE, the accuracy of your QPE in Taiwan is totally dependent upon the density of your rain gauges and your radar coverage. Okay? The poorer your radar coverage, the less dense your rain gauge network, the poorer your QPEs are going to be. Okay? So, you know, some of the challenges we have is that we have this area right here, we have very poor radar coverage. We also have very poor gauge density. This is an area where our QPEs are going to be very uncertain. There's other areas down here around Canteen, obviously up in these areas here. Now, so the challenge for us over the next 2 years is to try to continue to incrementally improve those QPEs, knowing that we have, you know, poor radar sampling problems, or we have radar sampling problems and we have, you know, some of those areas do not have a very dense gauge network. But can you do the QPEs using the radars by themselves? No. Can you do the QPEs accurately using the gauges by themselves? No. But together, very powerful tool. Very powerful tool. And again, Taiwan is perfectly positioned to be able to use those two remote sensing networks together to generate accurate QPEs that are needed. Thank you very much.
大家有没有问题？同学如果有问题，你用中文问就行。
You can ask him in Chinese. It just won't be answered in Chinese. Well, I asked Jin will answer it in Chinese. Jin is the chief scientist on this project. She is the person who's really behind a lot of the techniques that I showed, as well as the new system. And the work that she's done the last 3 years has gotten attention not only in the United States, but in Europe. And right now, the system that she's developed over the next year is going to be implemented at our National Center of Environmental Prediction. So a lot of the credit goes to her for this. Now, the errors and the bad things you can blame me for, okay? Because I'm the one who pushed her to do these type of techniques in this very challenging environment. Because, quite frankly, in the United States, it's not as hard as the problems you have here. So Paul, who's sitting back in the room, has heard me say this for the last 5 years. If we can do good QPEs here in Taiwan, we can do them anywhere in the world. Okay? All right, thank you.
Think we can we do have chance like
我这边忘了介绍一下张建博士，他也是那个 Chief Scientist， 他以前我在OU念书的时候，我们是同学，一阵子还一样的，同样的指导老师。那10年过来，我头脑都大了，所以台湾工作是很累的。
I also like to comment 那个邱台光哈，跟他们的 team， 像那个张宝亮啊，还有几位其他人，他们在这个工作是一起合作的，是台湾跟美国 SS 一个合作的。我相信这边学生如果有兴趣，也可以去他们那边跟他们几个，就不管到气象局，或者是到他们的单位去合作，他们会欢迎短期的访问。You know what I'm doing?
Yeah, he's been absolutely instrumental for all your work.
As a student, you also can visit your center and join this 2DE. And actually, because we have this radar, and I hope for the first one, we can cross comparison, calibrated. I need students to get in to really do the hard work. Okay. So I'm also here. I like student knows your team will be very, I think can be instructive to them, for them to learn with each other. We can work out better, even better than that. That's our goal.
Yeah.
Get a better than in many ways.
Yeah.
I think I have a few comments, maybe 3 or 2 more.
Yes.
Actually, we have 8 radars in Taiwan. We do have a radar in Green Island, but that one belongs to the Air Force.
Right.
So it is possible to talk with the Air Force, so we can use all the radar data instead of only 4.
Right. The infrastructure that's being set up in CWB can accommodate more radars. It's just a matter of getting the permission and the policy to be able to get the data. But the CWB system is set up to be able to integrate all 8 radars if they're available.
And you mentioned about the cross comparison between the dual pole QBE and the part of QBE stuff. How about inject the dual pole data into the QBE?
We would like to do that. Definitely.
How are you planning to do that?
Well, right now the system is set up to bring in the dual pole parameters, the KDP, the differential. So the system will be able to bring those in and display them. The first thing that we want to do is we want to do a cross comparison between the reflectivity field. Because the dual polarization, in effect, as you know, can be a self-calibrating radar. Well, the non-dual polarized radars can't be a self-calibrating. So you can take your dual polarized radar as a self-calibrating radar, then you can start cross-comparing it with the other radars and start calibrating those radars better. So that's the first thing that we'd like to see done over the next year to 2 years is, yes, bring in the dual polarized radar, but help first be able to do a cross-calibration. So.
同学有没有问题？
老师讲给学生听。
I need to push one student to raise.
Okay, let's do it.
Well, he can ask a question.
Yeah.
We know the QBE sum system use the composite radar data to do the QBE, but as I know, the composite radar data actually coming from different altitude, right?
Comes from
the composite data actually coming from a different altitude.
Yes, it does. We use what we call the hybrid scan reflectivity. Okay, the hybrid scan reflectivity is the lowest non-blocked beam associated with the radars. And if you'll pardon me for a quick second, I'll bring it up and show you what it looks like. This is the verification system, an early prototype of the verification system that we brought up for Taiwan. This is the actual height of the hybrid scan over Taiwan, and this has only got 1-2 pinching radars not in this. This is a dynamic product in that it continually updates the hybrid scan coverage pattern based upon which radars you're in. So in other words, if the Ken-Ting radar drops out, then these 2 radars start trying to fill in for it. And so the system that we'll be working with the CWB to install does the QPEs slightly different than the traditional mean. Right now, you take a single radar, you take the hybrid scan reflectivity, and you assign a Z on. The system that we're going to be upgrading, the QPE systems we're going to be upgrading, what it does is it takes the reflectivity from all of the radars and generates a 3-dimensional mosaic of reflectivity. It is then that 3D mosaic reflectivity that we determine the type of precipitation we think is falling, and then assign a differential ZR relationship to it. So in the beginning of my presentation, I showed you that precipitation flag field. We'll be doing the same thing for Taiwan. But it'll be primarily convective and tropical ZRs that will be used.
So is there any special treatment for data from higher altitude compared to lower altitude data?
Currently, no. What we will be doing is this first year we're going to be computing VPR. Do you know what a VPR is? Does everybody know what a VPR is? Vertical profile of reflectivity. It's basically if you were to take the radar dish and point it straight up, what does your reflectivity profile look like? We'll be deriving VPRs for all of the Taiwan radars to be able to try to understand the relationship of real high reflectivities to those that are actually occurring at the surface. So for example, the wall-in radar would be very interesting to compute a VPR to really understand what the higher level reflectivities are compared to what's happening at the surface. And then, can you extrapolate that vertical profile inland? That'll be the question. We don't know. I don't know. That'll be a nice research topic for a student. And we'll be glad to help them do that.
好，同学还没有问题。If no more question, that's where today's training. Let's thank Dr. Howard again. Thank you.
Okay, what's the first rule? First rule of hydrometeorology. Where does flash flooding occur? Where it rains the hardest and the longest. What's the first principle of nowcasting? Look out the window. Thank you very much.